because I have to catch a train. So I hope it's fine with you. Okay, so in last class, at last, we were discussing about the autoencoders. In fact, we were discussing the various deep learning architectures, and we started with supervised deep learning architectures, and we discussed mainly CNN and RNN, convolutional neural network and recurrent neural network. And then we started discussion of unsupervised deep learning models. And before this autoencoders, we discussed self-organizing maps. And at last, we discussed this autoencoders. And I told you that I'll tell you the benefits next time because we were discussing the other questions at last. So the benefits of autoencoders are many more over the other models, and that's why they are preferred today over the other deep learning architectures. So if I'll tell you in brief, like because there are several deep learning architectures which are based on autoencoders. So it's not one. In fact, we can say that it's a group of deep learning architectures which belong to, like there are several which belong to this group of autoencoder architectures. So for each model, the benefits are different, but if I tell you that which are the which are the benefits of this, then let me tell you in brief that one of the main advantage of using autoencoders is that they are flexible and adaptable to different types of data and tasks. Right? I hope you remember that in autoencoder based deep learning architectures, encoder and decoder are there. The job of encoder is to encode the data, input data, and job of decode is to reconstruct that encoded data and try to build the original input. So one of the benefits of this autoencoders is that they are flexible and adaptable to different types of data and tasks. And this autoencoders, they can handle both linear and non-linear relationships in the data. And they can learn complex or abstract features that other methods, other models may miss to learn. So that's why they are preferred. Moreover, autoencoders can also be customized by adding different layers, activations, regularizations, constraints to the encoder and decoder, depending on your problem and depending on the domain, depending on the goal and the challenges of the data. So you can customize it, right? By adding all this, like you can add different layers, activations, and so on. And if I give you example, you can use sparse autoencoders to enforce sparsity in the latent space or denoising autoencoders to remove noise from the input data. So just a simple example, like how flexible these autoencoders are. Now, these are benefits in general. These are the benefits of autoencoders in general. But as I told you, there are several types of autoencoders. Like if I tell you a simple autoencoders, or like if I tell you the different some of the types of autoencoders, then they are denoising autoencoder, sparse autoencoder, deep autoencoder, contractive autoencoder, which is used in architecture of unit model, which is based on CNN. Unit model. Later, you can search about the unit model. It is used for segmentation in computer vision. So this contractive autoencoder, it is used in this unit architecture. Then under complete autoencoder, convolutional autoencoder, variational autoencoder. So autoencoder is a head under which you have several types of autoencoders. So you can use all of them, and various architectures are available based on this autoencoders. So as I told you in last class, here I am simply introducing the major architectures of deep learning models, right? If you want to learn them in detail, then like you have to learn specifically a deep learning subject. Here we are learning deep learning for computer vision. So I'm not discussing all these models in detail. But if the subject title would have been like only deep learning, then we can discuss all these models in detail. But for computer vision, specific models are used, and we will discuss those models in detail, not all models. Fine. So I'm simply introducing the various models in this unit. Fine. So these are the major, benefits, and drawbacks are also there. Like I'll not discuss all the drawbacks, but the major drawbacks, if we discuss, then using autoencoders is that they are computationally expensive and they require more time and resources to train and tune the to tune like other than compared to other models, they require more time and to train your model, and they are computationally expensive too. Autoencoders are sensitive to the choice of hyperparameters. For example, how they are sensitive to number and size of layers. They are sensitive to learning rate, loss function, regularization, and these hyperparameters can affect the performance and quality of autoencoder, and may require trial and error to or grid search to find the optimal values for this parameters. Another drawback of using autoencoders is that they may not preserve the interpretability or the meaning of the latent space, and that makes it harder to understand what features or variables are important or relevant for the data. So these are the major drawbacks of autoencoders. Fine. So let's move forward then. After autoencoders, we have next model, restricted Boltzmann machine. Restricted Boltzmann machine. Okay. Though this RBMs, it is known as RBM, restricted Boltzmann machines. Though RBM became popular much later, they were originally invented by uh, Paul Smolensky in 1986. So these are also not new model. They were invented in 1986, and it was known as harmonium. This was known as harmonium. So this RBM is a two-layered neural network. The layers are input and hidden layers. As shown in this figure, the RBMs um, as shown in this figure, RBM's every node in hidden layer is connected to every node in a visible layer. And in a traditional Boltzmann machine, nodes within the input and hidden layer are also connected. Okay, in traditional Boltzmann machine. Due to computational complexity, nodes within a layer are not connected in restricted. And that's why its name is restricted Boltzmann machine. I tell you the difference between traditional Boltzmann machine and restricted Boltzmann machine. In traditional Boltzmann machine, nodes within the input and hidden layer were also connected. Okay, but it increases the computational complexity of the model. So another model was devised, and that was restricted Boltzmann machine. So connections were restricted in this restricted Boltzmann machine, and nodes within a layer are not connected in restricted Boltzmann machine. So you can see that like how the nodes are connected. During the training phase, RBM calculates the probability distribution of the training set using a stochastic approach. During training phase, RBM calculates the probability distribution of the training set using stochastic approach. And when the training begins, each neuron gets activated at random. Also, the model contains respective hidden and visible bias. While the hidden bias is used in the forward pass to build the activation, the visible bias helps in reconstructing the input. So two, like hidden bias is used and visible bias, two kinds of biases are used. So hidden bias is used in the forward pass to build the activation, and visible bias helps in reconstructing the input. Because in an RBM, the reconstructed input is always different from the original input. They are also known as generative models. right? So later, if you learn later deep learning, later versions of deep learning, you may learn this generative models. So this RBM, uh, it is also known as generative model. Also, because of the built-in randomness, same predictions result in different outputs. Same predictions results in different outputs. So this is the most significant difference from the autoencoder, which is a deterministic model. Just before this, we discussed autoencoder. Autoencoder is a deterministic model, while in this RBM, because randomness is built in this RBM, predictions result in different outcomes. As predictions result in different outcomes, like it is non-deterministic. Uh, determine the we cannot determine the performance of the model for the same input. I hope you know these terms, deterministic and non-deterministic. If not, then let me give you a simple example. Suppose it is square root function, right? You have implemented square root function in some programming language. Now you know that when it is square root function, every time you pass 9 as input, it should return 3 as the output, because square root of 9 is 3. Okay, so irrespective of number of times you execute that program, irrespective of number of times you pass that 9 as input, it should produce 3 for input 9. So if input is 9, the output should be 3 only. So if the algorithm is like this, then we can see that the performance of algorithm is deterministic, right? We can determine that for this input, the output would be this only. Every time you run that program, the output for 9 would be 3 only. So that is deterministic. But for the same input, if the output differs when you execute it multiple times, then the behavior of algorithm is known as non-deterministic. So same is the case here. This RBM is non-deterministic model, while autoencoder is deterministic model. Okay. So that's the difference between autoencoder and this RBM. And the use of this RBM is in dimensionality reduction and collaborative filtering. So wherever we use unsupervised learning, we use these models. So you must have observed that for autoencoders are also used in dimensionality reduction. But autoencoders are also used for data compression decompression because it is based on encoder-decoder concept. But this RBM cannot be used for data compression because here we are not using any encoder-decoder concept. But they both can be used for dimensionality reduction because these are unsupervised models, unsupervised deep learning models. Okay. So this is brief about this RBM, restricted Boltzmann machines. Now let's discuss deep belief networks. Like this is another unsupervised deep learning model or architecture. Deep belief networks. Deep belief network is a typical network architecture, but includes a novel training algorithm. In deep belief network, the deep belief network is a multi-layer network, typically deep and including many hidden layers. It includes many hidden layers, okay, in which each pair of connected layers is an RBM. Please look at this figure. In in DBN, each pair of connected layers is an RBM, that is restricted Boltzmann machine. In this way, deep belief network is represented as a stack of RBMs, stack of restricted Boltzmann machine, because multiple, like each pair of connected layer is an RBM. So multiple RBMs are there, and we can consider this deep belief network as a stack of RBMs. Okay, you can see in this figure, multiple RBMs are there. Okay. In deep belief network, the input layer represents the raw sensory inputs, and each hidden layer learns abstract representations of this input. Each hidden layer learns abstract representations of this input. Output layer, which is treated somewhat differently than the other layers, implements the network classification. I mean, it is like it is used for classification task, and training occurs in two steps. Training in deep belief network occurs in two steps: unsupervised pre-training and supervised fine-tuning. See the combination: unsupervised pre-training, and after unsupervised, like model is pre-trained. In which manner model is pre-trained? In unsupervised manner, using unsupervised learning. After that, in second phase, model is trained using supervised training. So supervised, it is called supervised fine-tuning. Supervised fine-tuning of the model. So in deep belief network, training is carried out in two steps: unsupervised pre-training and supervised fine-tuning. If I tell you briefly about these two steps, in unsupervised pre-training, each restricted Boltzmann machine is trained to reconstruct its input. For example, the first RBM reconstructs the input layer to the first hidden layer. The next RBM is trained similarly, but the first hidden layer is treated as the input or visible layer, and the RBM is trained by using the output of the first hidden layer as the inputs, and so on, because there are several RBMs, right? So you can see that the blue color box, the blue color box represents the first RBM, in which the input layer is the first layer, and the first hidden layer is the output layer. Okay, while for green color box, which is second, which represents second RBM, first hidden layer acts as input layer and the second hidden layer acts as the output layer. Similarly, for the third RBM, which is represented by red box, the second hidden layer represents the input layer and the fourth hidden layer represents the output layer, and so on, right? So this process continues until each layer is pre-trained. This process is continued until each layer in the model is pre-trained. When the pre-training is complete, fine-tuning begins. And in this fine-tuning phase, output nodes are applied labels to give them, output nodes are applied labels to give them meaning. Because at the end of first round, which is considered as pre-training, at the end of first round, you will have output for the input you have given to this model. So this output are then considered like as the labels, because what they represent in the context of input given to them. So these are the labels, and full network training is then applied by using either gradient descent learning or back propagation to complete the training, because the output of the first phase, they are considered, sorry, not first phase, first iteration, first training phase, they are considered as the label. They get associated with the input, and then it becomes a input output pair, and then this input output pair is used as label data to train this network in next iterations. So then it becomes like, when there is a label data, it becomes supervised training. And when it is supervised training, like of course for given input, the predicted output, the difference is calculated, and gradient descent or back propagation is used to to complete the training process. So this deep belief network, it includes two phases of training: pre-training and then complete training, fine tuning. Examples applications. Example applications are image recognition, information retrieval, natural language understanding, and failure prediction. This deep belief networks are used. Okay. Then next we have deep stacking networks. Deep stacking networks. Okay. This deep stacking network, which is final, network in our group of deep architectures. It is also called deep convex network. It is also called deep convex network, and it is different from traditional deep learning frameworks, in which, although it consists of a deep network, it is though it is a deep network, it is actually a deep set of individual networks. It is a deep set of individual networks. Okay, and each with its own hidden layers. It is a, a deep set of individual networks, and each network with its own hidden layers. And this architecture is a response to one of the problems with deep learning, the complexity of training. So to overcome that problem associated with deep learning, the problem of complexity in training. So to overcome this problem, this architecture was proposed. Each layer in deep learning architecture exponentially increases the complexity of training. In any deep learning architecture, each layer exponentially increases the complexity of training. So this deep stacking network views training not as a single problem, but as a set of individual training problems. It divides the problem into sub-problems. So this deep stacking network, it doesn't view training as a single problem, but it views training as a set of individual training problems. And then it consists of a set of modules, each of which is a subnetwork in the overall hierarchy of this deep stacking network. In one instance of this architecture, 3 modules are created for this deep stacking network, and each module consists of an input layer, a single hidden layer, and output layer. So you can see here the three modules are created. Like this is one instance of this architecture, okay? It is not only this architecture, one instance of this architecture. 3 modules are created for this. In this architecture, which I have represented using figure, in this architecture, 3 modules are created for deep stacking network. You can see that which are yellow color, green color, and blue color. They are represented by these 3 colors. Now you can notice that each module consists of 3 layers: input layer, hidden layer, and output layer. Fine. Modules are stacked one on top of another, where the inputs of a module consist of prior layer outputs and the original input vector. So look at this, like original input vector and the output of the previous layer. This layering allows overall network to learn more complex classification than it would be possible given a single model. So for single module, it would be difficult to learn for complex classifications. When there are 3 modules in the deep learning model, 3 different modules, it is kind of 3 different networks are there in this architecture. So it becomes able to learn more complex classification features. So this is how it is comparatively good than the other models. This deep stacking network, it permits training of individual modules in isolation. Okay, this is noticeable point. It permits training of individual modules in isolation, making it efficient given the ability to train in parallel. Okay, so training would be faster. 3 modules are there in our example architecture, blue, green, and yellow, and they can be trained in isolation. So they can be trained in parallel. So this increases the efficiency of the model. Supervised training is implemented as a backpropagation for each module rather than backpropagation over the entire network, right? It is supervised training is implemented for each module. So 3 modules are there. For each of them, supervised training is implemented. So we do not use backpropagation over the entire network. but for individual model. And for many problems, this deep staking network can perform better than typical this DBNs. So this makes them popular and efficient network architecture. Right. So this is brief about deep stacking network, and as just I told you, they are beneficial over deep belief networks. And application areas are information retrieval and continuous speech recognition. So these are the application areas of this deep staking network. So to summarize, we have seen this deep learning architectures, right? But if you want to expand this classification of deep learning architecture, you can, because there are several models available under autoencoders and other categories. So like today, many models are available, but these are the like, broad categories, you may say, and variations are available for each of this, right? But I have briefly introduced you various deep learning architectures which fall under two major categories: supervised learning and unsupervised learning. So as you can see, like among all this, in this subject, you will learn convolutional neural network. So rest of the architectures you will not be learning in this subject, right? Probably in next subject in series, you will learn LSTM and GRE, right? But not unsupervised learning, I think, right? So many architectures are available, but we have seen the major architectures. Okay. So any question till this point? Because now I'm going to start a new topic of this unit. You may also type your question in chat box. Today, I will not extend discussion beyond 6:25 or 6:30 because I have some other schedule. Yeah, let me check. No, it's not fixed here that there will be only 3 modules in DSN. It is as per our requirement and the complexity of problem or complexity of data set. We can increase the number of modules. Just for example, like 3 modules are included in this architecture. DSN means DSN. Okay, like wherever we use the concept of supervised and unsupervised, rather I tell you that the previous architecture, deep deep belief network, wherein we conduct training in 2 phases: pre-training and supervised. This is like a very good example of semi-supervised. It is kind of semi-supervised, yes, because first we pre-train the network, labels are generated which are called pseudo labels, and in next iterations those pseudo labels are used as label with the input data, and that label data is used for fine tuning. So wherever we use like supervised and unsupervised concept, it is semi-supervised learning. Yes. Okay. So if no more question, then I can. Okay, let's move forward then to next topic. Okay, then in your module, these are things actually, I tell you. Yeah, deep learning and its architectures, then activation functions and hyperparameter tuning. So this we discussed in last unit, in previous unit, and the concepts are same because whichever concepts you apply to machine learning models, they are same for deep learning models also, because deep learning is subset of machine learning. So sometimes additional things are available, but they are whatever concepts you have learned for machine learning, they are applicable to deep learning models also. So I'm not repeating those topics: activation functions and hyperparameter tuning. Supervised and unsupervised deep learning, like it is again the kind of learning using which deep models can learn. So supervised, unsupervised, semi-supervised, self-supervised. So different types of learning techniques are there, which we discussed many times. So I'll not repeat them. And the next topic is how can you improve your deep neural network? So let us discuss now that how can we improve the performance of deep neural network. So the first is bias versus variance trade-off. So let's discuss it. Okay, bias versus this variance. Yeah. Actually, in machine learning, error is a measure of how accurately your model can make predictions for the previously unknown data set. How accurately model can make predictions for the previously unknown data. On the basis of these errors, machine learning model is selected that can perform based on the particular data set. So there are many machine learning models. And as I discussed earlier, like you cannot choose a particular model for a particular data set or particular problem. You need to experiment with different models and you need to check that which model, which machine learning algorithm is giving you good performance for your problem, for your data set. And then you have, like, you can conclude after exhaustive experimentation that so and so model is good for this problem or for the problem, right? So there are mainly two types of errors in machine learning, which are as shown in this diagram. They are reducible errors and irreducible errors. So machine learning algorithms, uh, they have these two types of errors. Reducible errors are the errors, like they are these errors, reducible errors, they can be reduced to improve the model accuracy. And such errors can further be classified into bias and variance because they can be reduced by some ways. Okay. And irreducible errors will always be present in your model. They cannot be reduced. So there's two kinds of errors machine learning models have. Similarly, deep learning models, they have these errors, reducible errors and irreducible errors. Okay, so regardless of which algorithm has been used, you have this like errors will be present in model. The cause of these errors is unknown variables whose value cannot be reduced. Okay, so that is the cause of this errors. Okay, now in reducible errors, bias and variance, these are the two types of errors. So let us first see what is bias. Okay. So, okay, fine. So as you can see, machine learning model analyzes the data, find patterns in it, and make predictions. While training, the model learns these patterns in the data and applies them to test data for prediction. So this is how they work. Now, while making predictions, a difference occurs between prediction value made by the model and the actual value which is there in the data set. And this difference occurs between the predicted value and the actual value. And this difference is known as the bias error or error due to bias. Now, this bias, it can be defined as an inability of machine learning algorithm, such as inability of linear regression to capture the true relationship between data points. So each machine learning algorithm begins with some amount of bias because bias occurs from assumptions in the model, initial assumptions in the model, which makes the target function simple to learn. So model has either low bias or high bias. Model may have either low bias or high bias. Okay. So what is low bias and what is high bias? A low bias model will make fewer assumptions about the form of the target function. Low bias makes fewer assumptions about the form of the target function, and high bias in high like a model with a high bias makes more assumptions, and the model becomes unable to capture the important features of our data. So high bias model also cannot perform well on new data. It cannot perform well with the new data. Fine. Generally, a linear algorithm has a high bias because it makes them learn fast. Simpler the algorithm, higher the bias it has likely to be introduced. Whereas non-linear algorithm, which are complex, which are considered complex algorithm. Okay, linear algorithm is considered simpler algorithm, and they usually have high bias. And non-linear algorithms, which are considered complex algorithms, they introduce low bias. They often introduce low bias. So I give you some examples of machine learning algorithms with low bias and high bias. Decision tree, those who have learned machine learning, they might be knowing this algorithm. Decision tree algorithms, k nearest neighbor, support vector machine. This algorithms, they have low bias because these are non-linear algorithms. At the same time, an algorithm with high bias are algorithms with high bias are linear regression, linear discriminant analysis, and logistic regression. These are simpler algorithms, but they have high bias, right? So this is what the bias is, and let me also tell you that how this high bias can be reduced. How this high bias can be reduced. So these are the different ways to reduce the high bias. High bias mainly occurs due to much simplicity in model. And here are the ways to reduce the high bias. We can increase the input features as the model is underfitted. So the problem of underfitting occurs when there is high bias. If you remember, we discussed these two problems, underfitting and overfitting with machine learning models. So underfitting occurs when there is high bias. Okay, so we can increase the input features as model is underfitted, and when model is underfitted, like you can say when there is high bias, underfitting problem occurs. So we can increase the input features because model is underfitted. We can decrease the regularization term in model, and we can also use more complex models such as including some polynomial features. Because the model is simple, this underfitting occurs and high bias is introduced. So if you want to reduce it, you can have more complex model. So these are the ways to reduce high bias. Fine. Okay, now let us talk about the variance. Low variance, like, okay, variance, we discuss what exactly the variance is. The variance would specify the amount of, it specifies the amount of variation in the prediction if the different training data was used. In simple words, variance tells that how much a random variable is different from its expected value. How much a random variable is different from its expected value. Ideally, models should not vary too much from one training data set to another. From one training data set to another, models should not vary, which means algorithms should be good in understanding the hidden mapping between inputs and output variables. So variance errors are either of low variance or high variance. Low variance means there is a small variation in the prediction of the target function with the changes in the training data set. When you change like data set, the prediction in variation variation in prediction is small, that is low variance, and high variance shows a large variation in the prediction of the target function with the changes in training data set. When you change the training data set, uh, like it will produce large variation, right? So that is called high variance because there is a variation. So variation is large, so high variance. If variation is low, it is low variance. A model that shows high variance learns a lot. It overlearns. A model that shows high variance, we can say it has overlearned. It learns a lot and it performs well with the training data set and does not generalize well with unseen data set and that's why the variance is high. For training data set, it performs very good. But for unseen data set, it does not perform good. So we can say that the model has not generalized good. Because of this, a model gives good results with the training data set, but shows high error rates on the test data set. High variance means what? Model shows good performance for training data set, but model does not perform good for the testing data set. It is unseen data for which it does not perform good. Because with high variance, the model learns too much from the data set, it leads to overfitting of the model. It leads to overfitting of the model. Okay. And a model with high variance has the problems like a high variance model leads to overfitting and it increases model complexity. It increases models complexity. So these are the problems with it, and we can reduce high variance. So these are the ways to reduce high variance. Okay, before we discuss the ways to reduce the high variance, let me give you examples of models which show low variance and high variance. Linear regression, logistic regression, linear discriminant analysis, they show low variance. While decision tree, support vector machine, k nearest neighbor, they show high variance. Okay. Now I hope you are with me. So if you are with me and if you have observed, all the models which show high bias, they show low variance. And all the models which show low bias, they show high variance. And that's why here we are discussing the trade-off between this bias and variance. Okay, I repeat, all the models which show high bias, they show low variance and vice versa. Okay, so let us see the ways to reduce this high variance. We can reduce the input features. Okay, remember the ways to reduce the high bias. There we increase the features. Here we reduce the input features or number of parameters as model is overfitted. Their model was underfitted. Here model is overfitted. When model is overfits, when it learns too much. So when it has learned too much, we need to reduce the input features because it's learning too much. While to reduce the high bias, when it introduces high bias, when it learns, when model is underfitted means it has not learned good. And then when we need to increase the input features. Fine. Moreover, how can we reduce high variance? We do not use a much complex model. It is again reverse of that of the way we discussed to reduce the high bias. Okay. Moreover, we can increase the training data and increase the regularization term. So these are the different ways to reduce the high variance. So I hope the trade-off between these two is clear, that how when bias is high, variance is low, and when bias is low, variance is high. So here are the different combinations of bias and variance. 4 possible combinations, of course, with bias and variance. High, low, high, low. So 4 combinations are there. Low bias, low variance. Okay, low bias, high variance. high bias, low variance, and high bias, high variance. Such four combinations are possible with these two terms, high bias and variance. Okay. So what is low bias, low variance? Please understand this. The combination of low bias and low variance shows an ideal machine learning model. However, it is not possible practically. Low bias, what does it mean? It is not underfitted. Low variance, it is not overfitted. Low bias, not underfitted. Low variance, not overfitted. So model has generalized good, right? So this is ideal model actually, but practically it is not feasible. Okay. Low bias, high variance. High variance आ गया, उसका मतलब overfitting आ गया. Okay. High bias means underfitting आ गया. So that is a problem. So low bias, high variance. With low bias and high variance model, predictions are inconsistent and accurate on average. Okay. And this occurs when the model learns with a large number of parameters and it leads to overfitting. The low bias, low variance. Next is low bias, low variance. Of course, when bias is high, underfitting occurs. So again, there is a problem with this model. Generalization is not good. So with high bias and low variance, predictions are consistent but inaccurate on average. This case occurs when a model does not learn well with the training data set or uses few number of parameters, and it leads to underfitting problem in the model. Fine. So one is high and one is low. It's not a good case. Either it leads to overfitting or underfitting problem. Both are low, it's ideal. Model is ideal. And when both are high, right, with high bias and high variance, predictions are inconsistent and also inaccurate on average. So this is also not good case. Okay, so the trade-off between this bias and variance. Okay, just let me tell you that how can you identify the high variance or high bias in model? So high variance can be identified. High variance can be identified in the model if the model has like when you compute error, test error. So when a training error is low, but the testing error is high. So that results in high bias. Sorry, yeah. Like, okay, low training error and high test error. Sorry, low training error and high testing error. And high bias can be identified if high training error and testing error is almost similar to training error. Then we can identify high bias in the model. And for trade-off, like graph can also be drawn. If we decrease the variance, it increases the bias. And if we decrease the bias, it increases the variance. Because they go in different directions. So if you increase the variance, right, it decreases the bias. And if you increase the bias, it decreases the variance. So this is the trade-off between these two parameters. Fine. Okay, so now if you have any question, this is all about the bias and variance. If you have bias variance trade-off, we can discuss. Bias variance trade-off is about finding the good spot to make a balance between bias and variance errors. That's the goal. And that's why bias variance trade-off is considered while training the model, because it helps us to find sweet spot to make a balance between bias and variance errors. Okay. You may type your query or you can unmute and let me know your query. Any query? So if no query, then I'll not start a new topic today. And I'm very sorry to, you know, conduct like till 10 minute late. Okay, but it's okay for one day, I suppose. Yeah, it's okay.